Hey everyone, and welcome. Today we're going to jump right into the world of chemistry, specifically for Class 10. We're going to look at the huge differences between metals and nonmetals, and figure out how their tiny atomic personalities decide how they act, and, just as importantly, how we get them out of the ground. So let's kick things off with a little bit of a puzzle. Have you ever wondered why you can find gold just lying around as these beautiful, pure, shiny nuggets? But iron, which is one of the most useful metals we have, is always trapped inside some rust-colored rock. Well, the answer to that question is really the key to understanding all of this. And by the end of this explainer, you're going to know exactly why that is. Okay, so to solve our whole gold versus iron mystery, we've got to shrink way, way down to the atomic level. We need to ask a really basic question first. Why do atoms even bother reacting with each other in the first place? Well, it really boils down to one simple thing: stability. You can think of atoms as just wanting to be perfectly balanced, or content. In chemistry, the most stable elements are the noble gases, like neon and argon. They have a completely full outer shell of electrons, which makes them super unreactive. They just don't need to interact with anyone. Every other atom out there is basically trying to get that same stable setup. Okay, take a look at this table with me. It shows exactly what we're talking about. See sodium over there, a classic metal? It's got just one lonely electron in its outermost shell. Now, it's way, way easier to just give that one electron away than it is to try and find 7 more to fill the shell. Now look at chlorine, a nonmetal. It has 7 outer electrons. It is so close to having a full shell, it just needs 1 more. You can probably see where this is headed, right? And that whole dynamic, you've got the metal that wants to give an electron away and the nonmetal that desperately wants to take one. That sets the stage for one of the most powerful connections in all of chemistry, the ionic bond. Now, the most important word here, guys, is transfer. This is not about sharing. The metal completely gives its electron to the nonmetal. So what happens? By losing a negative electron, the metal atom becomes a positively charged ion. And by gaining one, the nonmetal becomes a negatively charged ion. And what do opposites do? They attract. Just like magnets, they stick together with this incredible force. And that is the ionic bond. And here it is. This picture shows our example perfectly. You can literally see that electron making the jump from the sodium atom right over to the chlorine atom. Poof! Sodium is now a positive ion, and chlorine is a negative one. And the best part? Both of them now have what they wanted all along: a full, stable outer shell. It's a total win-win. So, what's the result of this little transfer? Sodium chloride, which you and I just called table salt. But stop and think for a second about how absolutely wild that is. We start with sodium, a shiny metal that literally explodes if you drop it in water, and chlorine, a poisonous gas. But when they form this ionic bond, they create this stable, harmless crystal that we sprinkle on our food. That is the amazing power of chemistry right there. So now that we get how these ionic compounds are made, what are they actually like? What kinds of properties do they all share, all because of these super strong bonds? Well, it all goes back to those bonds. They're hard solids because their ions are locked into this really tight crystal grid. They're often brittle because if you hit them just right, you can shift the layers, and suddenly ions with the same charge are next to each other, they repel, and the whole thing shatters. And this is a really important one. As solids, they do not conduct electricity. The ions are stuck. They can only conduct when those ions are free to move around, which only happens when you melt them down or dissolve them in water. And hey, if you need proof of just how strong these bonds are, just look at this chart. The melting point of plain old table salt is over 1,000 Kelvin. That's more than 800 degrees Celsius. It takes a massive amount of energy to break those ions apart from each other. And this brings us right back to the beginning. We now get why reactive metals form these compounds out in nature. So, how do we go backwards? How do we break those powerful bonds to get the pure metals back from the rocks we dig up? Okay, this chart right here is the absolute key. It's called the activity series, and it's basically a ranking of metals from the most reactive up at the top down to the least reactive at the bottom. Where a metal sits on this list tells us everything. The higher up it is, the more stable its compounds are, which means the harder it's going to be for us to get that pure metal back out. Now, this flowchart, it might look a little complicated at first, but trust me, it's really just the activity series we just saw, but turned into a game plan. It splits metals into 3 groups: low, medium, and high reactivity, and it shows us that the method we use depends entirely on which group the metal belongs to. So let's just walk through it. Let's start at the bottom of the series with the easy ones. We're talking about the least reactive metals, like gold and silver. They're so unreactive, you could even say lazy, that they often don't even bother forming compounds at all. They can just be found in their pure native state. And that's exactly why we find gold nuggets. All right, moving up into the middle of the pack. This is where we find our friend iron, along with others like zinc and lead. These guys are found in compounds, like carbonates or sulfides. To get them out, first we have to heat the ore to turn it into a simpler form, a metal oxide. We call that roasting or calcination. Then we use something more reactive, like carbon, to come in and basically steal the oxygen away, leaving us with the pure metal. And finally, at the very top of the series, we have the super reactive metals, like sodium and potassium. They are so reactive, they form these incredibly strong bonds that even carbon can't break. For these guys, we have to bring out the big guns, electrolysis. That's where we use a powerful electric current to literally force the electrons back onto the metal ions, turning them back into pure, shiny metal atoms. So there it is, that's the answer to our puzzle. Gold is found as pure nuggets because it has such low reactivity it almost never forms compounds. Iron is found as rusty ore because its medium reactivity means it loves to bond with other elements, and it takes a whole industrial process to break that bond and get it back. A metal spot on the activity series really does decide its fate. I really hope this explainer helped connect all these big ideas for you. For more helpful breakdowns on your Class 10 science topics, you should definitely subscribe to the A1 Institute on YouTube. Thanks for watching.